Hey everyone, welcome back to episode 2 in this series where we're explaining transformers. Last time we explained encoder models like BERT. This time we're going to be explaining decoder models like GPT-2, 3, and so on. This should be a lot shorter because there's much less that I need to explain. And it should look pretty familiar. I'm trying to introduce you to kind of a pattern that you can follow for this, for making your own things. So we're starting out by making our IPYNBs. Just a quick side note, IPYNBs are fantastic for experimentation and research in Python because it allows you to run cells of code that do one thing instead of an entire script at once. It makes debugging a lot easier. However, you're going to want to get familiar with converting back and forth between IPYNBs and actual Python scripts, because IPYNBs are much harder to deploy in a really nice, scalable, robust way, whereas scripts you can. So we're going to create that GPT Kant folder. You'll notice this is that same Kant dataset as last time. We're going to be doing almost the exact same thing, except instead of training a model that is made just to fill a mask, which is what BERT does. This is where you can see the real difference between BERT and GPT models, difference between encoder and decoder models. Encoder models are made for some sort of a classification or guessing one thing, right? You can use them for other things, but that's what they are really good at. That's where they shine. GPT models and decoder models, by extension, are much better at generating a lot of things at a time, and that's helpful for us. So let's jump right into it. So for this, we're just going to need transformers, torch, and datasets. We're going to do the GPT-2 tokenizer instead of the BERT tokenizer. You can also use auto tokenizer for this if you'd like. LM head model, because we're going to be doing language modeling. We're going to want the config so that we can change things up. We're going to want data collator for language modeling to fit everything together. We're going to want training arguments and trainer. And these are both really helpful APIs for us. And then from datasets, import load dataset. And then import torch. So our data set is going to be exactly the same as last time. We're going to load the data set, and it's going to be text and data files equal Kant.txt right here in this folder, and then data set equals dataset.filter. So if you aren't familiar with Lambda functions, let me tell you right now, they're extremely useful. They allow you to create a function inline on the fly and just use that function once. You don't have to save it anywhere. It's really helpful for this. In our case, because GPT is a little bit more fussy than BERT is about not only sentence length, but vocabulary, being a decoder model, it needs more than empty spaces. And here, let's do this so that I can show you. So print dataset train, and we'll just print the first, and then we'll comment this out. Right, so it's loading up the dataset really fast. This should take a couple of seconds. And we can finish this while it's happening. But so here we go. This is the first sentence in our data set, right? It's just an empty space. So we want to get rid of those. And the way that I've come up with to get rid of them, and you can and should probably do a lot more filtering on this. I'm not going for completion on this. I just want to show you how it's done. So we're only going to take the sentences where the text is greater than 1. And so print len dataset train. Oh, oops. We do want to copy it though, and then we want to see how much actually gets taken out. So we've got 188,000 and then 117,000. So about 18,000 of our sentences were actually just straight space. Anyway, we'll come back to that later. So let's instantiate our model. We're going to do it the same way as before. And you don't technically have to do this. However, I find it's a lot easier to instantiate using custom configs every time, just to get in the habit of it so that we can make things better than they were before or in the original paper, or in our case, we're going to be using GPT-2, as we said before. The reason we're using GPT-2 is because it's a lot smaller than GPT-3, and I wanted to make this something that you could do on, like, 8 or 6 gigabytes of RAM, so you don't need 12 or 24. I'm not expecting every single one of you has a 24 gig 3090 on your rig. So in order to make this accessible, we're going to make it even smaller. So vocab size. In the original paper, we have 50, 20, 57. 50,257 is the vocabulary that's in the original paper, so we're just going to keep it at that. Number of positions. So this is this is the max length that it can take. And in the original paper, it's 1,024. We're going to cut it down to 256 because, I want this to not take a significant amount of GPU memory so that you can actually train this if you want to. If you want to do the full 1024 and your GPU is not good enough, I'm going to show you down later how to make sure that you're running this on a CPU instead of a GPU so that you can take the whole thing. Just know that it will be a lot longer. It's going to take a really long time to train on CPU. There's ways to optimize it. The number of embedding dimensions is 768. This is the exact same as BERT. It's a number that you'll see a lot when you're working with language models. It has to do with word to vec and positional embeddings. And then activation function. I like changing this to GELUs instead of RELUs. I think that they're better for especially generation tasks. But this is the config that we're going to use, and I'm going to show you exactly how to load models that have a different config than the model that you're actually loading, especially a pre-trained one. So tokenizer equals GPT-2 tokenizer from pre-trained, and then just GPT-2. We're just using the actual one from OpenAI. Something special about this tokenizer is it does not have any special tokens. So, similarly to our BERT tokenizer that we trained from scratch, again, also, you should know, this GPT-2 tokenizer under the hood is a byte-level byte pair encoding tokenizer, which is exactly the same custom one that we did in the encoder video. So if we want to, or if you would like to, you can do the exact same thing. You can train a brand new byte-level BPE tokenizer on your dataset, and just remember to add these tokens to it. First one is the beginning of sentence token. I'm gonna just copy this because I have it right over here. And we don't need to type it all out, but what we do need is to know what all of these are. Beginning of sentence token, end of sentence token, padding token, and mask token. These are the two most important ones to add because, like I said before, GPT-2 is pretty picky about the input length that you give it during training. All of them have to be the same length. Otherwise, it's going to have a lot of trouble. Dot add special tokens. And then we're going to do mask token because I am going to show you how to train this masked language modeling style, which is exactly the same that we did the encoder model with. I want to do that so that you can see that these models really are interchangeable, and it's less about the model and more about understanding the problem that you're trying to solve and understanding the tools that are at your disposal that are really going to empower you to be a good machine learning engineer or data scientist or a research scientist. This should help empower you to do your job very well. GPT-2 LM head model, and from pre-trained we're going to do GPT-2 and config equals config. Okay, I'm going to do this and it's going to error out because I want to show you exactly how to actually change that config when you're loading a pre-trained model. This allows you to change models that you've already changed or already trained on the fly. You do have to train them every time, and it's going to pass a warning for that. But this should help you if you ever run into this error. Size mismatches, right? Our first size mismatch is 1024 by 768. We're passing 256 by 768. These numbers should seem familiar, 256, 768. So the original number of positions is 1024, and it's getting mad because that matrix multiplication doesn't work initially while it's testing it because it's expecting 1024 and it's getting 256 in every single one of these places. But it gives us this nice little argument that we can add, which if we just copy and paste it, ignore mismatched sizes equals true, all of a sudden it will pass the warnings, but it will not error out. And then it gives us this warning. You should probably train this model on a downstream task to be able to use it for predictions and inference. This is because this original matrix multiplication is still present in the model. Just because we changed the config does not mean that we changed any of the weights. That's what we're actually adding. We're loading this right here. We're loading the initial weights, and the weights rely on this matrix multiplication. So why don't we train it? So we're going to do the same thing that we did before. We're going to write a nice little tokenized function for our batch. And it's going to be literally the same thing. So return tokenizer string batch. This is where things get a little bit different, actually. I shouldn't have said it's going to be exactly the same. Our padding is going to be 2 max length, meaning if it is lower than 256 in length, it's going to be padded all the way out there. And our truncation is definitely going to be true. If we don't do these things, we are going to run into issues with that matrix multiplication. And then the max length is 256. Perfect. And then our encoded dataset is going to be dataset.map tokenize batched equals false. And then we're going to print ds train and 0 to see how this sentence ends up looking in our dataset and to make sure that it worked. So this should take about 30 seconds to do. Just in case you're unfamiliar with this, and this is your first, you didn't see the first one, what we're doing is we're providing an encoded embedding for each one of these sentences in our data set. Because machine learning models cannot handle textual input, we have to convert the text into numbers, same as it can't handle pictures, so we convert those pictures into numerical form. By that's what we mean by encoding. And this is what that looks like. The encoding comes out to input IDs and attention mask. Those are the two things that our model really needs. in order to do well. So next part is the data collator to make sure that it's organized going into the model. Data collator for language modeling. Tokenizer is tokenizer. MLM is false. MLM probability is 0.15. You can do MLM on this if you would like. All you do is change that to true. It doesn't really matter because it's going to, like, the task that it's training on is guess the next word, which works really well for generation because you just have it loop that task several times and go figure it guesses multiple words while appending the previous guess to whatever you had input. So training arguments. I think that I did training args in the first video, so I'm gonna do that here. Training args. Output directory. This is where the model gets saved to. We want to save it to our GPT Kant folder. Oh, I need a comma. We only want one training epoch. This is a really important parameter. I have set it to, I'm going to set it to 8. I know that my GPU can handle 8. If you run into memory issues, you may want to consider changing this and changing your max length up here. Oh, also, shoot, I forgot about this. Because we are adding 4 tokens, we need to change our vocabulary size. We need to add 4 to 50,261. If we don't, this end of sentence token is going to give us errors on every single one, because you noticed 50257 was the number, and 50259 is present in every single one of these, right? And so you're immediately going to get an index out of range if you don't make sure that that vocabulary is different. I'm actually gonna rerun this just so that we have it, making sure that, yeah, and we get that same error with the vocab size. That's okay. We're adding 4 tokens into our vocabulary. And then after our per device train batch size, save steps, I do 5,000. You can do lower, you can do higher. That just tells it how often to save checkpoints to the model. If you want to do it every 100 steps, you can do that. And then this allows you to truncate how many of those actually get saved. So let's say you have 3 models already saved, it's still training, and then it goes to do a 4th one. If this number is 3, it's going to delete the oldest version of them. This is good for rolling training and training off of checkpoints and training on multiple tasks. It's not as good if you want to keep every single iteration and then do some really serious hyperparameter tuning. If you want to do hyperparameter tuning, then just delete this. Now we'll get into that in later videos. Report 2 equals none. This is not a sponsored video, and I don't want anybody to just automatically know that you're training things. Model equals model. Args equals. This, it's so annoying. Okay. Data collator, and then our training data set. Now, again, I've mentioned this before, but were this an actual scenario, I would have 3 different data sets, and I would use a function called train test split to get those. Generally, you want training to be like 75% of your data set, validation to be about 10% of your data set, and then test to be about 15% of your data set. This is a really nice way of splitting things up. What this would entail is then you have an eval data set. And yes. Usually it's just val. And then you would have a test data set that's this. What happens is every time you hit your validation number in your training steps, it will then take time to validate the data set. This helps the model know whether it's overfitting or underfitting. It helps it algorithmically. This is something that you should do if you're doing this for real. I just want to show you how these APIs work and how to train these things, so we're not going to do it. Trainer.train. Again, if you have a checkpoint, you'll put in like GPT can't checkpoint 10,000 or whatever, and then it will skip it, and you input that as a, it'll skip up to that point, and you enter that as a string. Trainer.save model. And this takes a long time, and so what I'm going to do is actually just import these models that I already trained right in here, and it's going to take a little bit because especially that PyTorch model.bin, it is a large model. And oh, where is it? I'm going to show you exactly how big that is. Yeah, so our model.bin is like 0.5 gigabyte. These end up being a lot bigger. One of the reasons it's so small is because we truncated how big of a input the model can have and everything. So we're not going to do this right this second. And then actually, I think that's it for this. Once you've trained this, it gets saved, and then you have the model right here. You can then load the model by doing model equals GPT-2 LM head model from pre-trained, and then inputting GPT can't. And then this is the really cool thing. I didn't show this in the first video, but I'm going to go a little bit more in depth in the next video. If you want to do something really cool, I'm just gonna do this right here. Because we're gonna dive into this, I would say just copy and paste this for now, and then I'll tell you more about what all of this means. Harry Potter and Hermione, blah. Right? So this is going to grab the exact model that we trained. You know that it's the same one because we have our embeddings. We have our number of positions is the same as 256. Our GELU activation function is GELU, right? And then here, using model.generate, you take the input, you tokenize it, and you'll notice we're not adding any padding. We're just returning it as tensors. This is how you tokenize your inputs when you're actually testing the model and want to generate it. And then model.generate, it takes input IDs, it takes attention mask. We're gonna jump into what all of this is. Max length 256, you want to keep that the same as the model. Beams are interesting. They allow you to pick from several different options every time it's generating. Temperature allows you to determine how random things are. Top K allows you to look at like the top number of responses or the top number of probable responses that the model is generating and pick from amongst those. Top P allows you to look at the top probability of those using a softmax. Really, really cool stuff. We're going to jump into what all of these mean. This is the most important one for our model. No repeat n-gram size equals 2, meaning that this tries to repeat things only tops 2 times and not more. Harry Potter and Hermione, I see, on the conception of the object, for we are at the same time we should merely the series. So it doesn't make a lot of sense. This makes sense because we only did one epoch in our training, and we're severely limiting the model and its ability to do things. This gets better if you do more epochs. It gets better if you add length to it. It gets better also if you add a good optimizer like Atom W or stochastic gradient descent. But yeah, this is it for this model. The next one that we're going to do is an encoder decoder model. We're going to be looking at T5. So I'll see you in that one. See ya.